Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a review video for those who are reviewing factoring techniques from their previous algebra courses. It's for those who are currently enrolled in, that is, a college algebra class. You could actually go through and search the web for a bunch of different videos on how to factor this, how to factor that, whatever it may be. But this single video covers pretty much all the prereq factoring techniques that are super important for college algebra and then for calculus. So we'll start this video with a very simple question. Why do we factor? Well, the reality is we factor very commonly outside of mathematics. In fact, we factor in language all the time. In fact, with a sentence like this, student A is wearing pants, student B is wearing pants, and so on and so forth down the line until we get to student Z, and student Z is also wearing pants, we would never say it that way. Oh, student A is wearing pants. Oh, student B is wearing pants. Oh, student C is wearing pants. We'd be there all day saying that. So instead, we say something like, all of the following students are wearing pants. A, B, C, D, E, F, and so on and so forth all the way until we get to Z. We have factored out the common phrase, is wearing pants. And we're saying just apply that trait to every single person in this group. And that is language factoring. We do it all the time. So why not do that in mathematics? If you have a lot of terms that share something in common, why not just look at that and say, well, what do they all have in common? I can easily see this first term has an x in common with the second term and in common with the third term in line. You would not say they all have x cubed because they don't all have x cubed. They all have at least x, but not x cubed nor x squared. So you take the minimal amount that they share in common. So in this case, I would just say each of these objects has an x in common. And if you factor that x out, you'll be left with 3y plus 2xz plus 4x squared k. So you obviously know how to factor because you're in a college algebra class, but that's why we actually factor. We're trying to reduce the amount of repeatability in what we say. We do it all the time in language, and we'd like to do that in mathematics. Now, that's the superficial reason as to why we factor. However, there's a really great mathematical reason as well. We like to factor because when you have an expression in factored form, it's much easier to evaluate that expression. Take, for example, this expression I've just written right here. If I were to ask you to evaluate that expression at something very simple, let's just say at x equals 1. If I were to ask you to evaluate that at x equals 1, a lot of people actually would sit there and say, okay, 3 times 1 squared plus 1, and then we're going to multiply that by 1 to the 7th, minus 2 times 3 times 1 squared plus 1, right? There's just a lot of handwriting involved. But if you pre-work the problem and just do a little bit of handiwork beforehand and notice each of these terms here and here have a 3x squared plus 1 in common, you could say the following objects have 3x squared plus 1 in common. The objects are x to the 7th and a negative 2. And now evaluating this at 1 is just going, I'm not going to say equals, but I'll just say evaluating this at 1 would be 3 times 1 plus 1 times 1 minus 2. Very fast, right? And so that's why we end up using factoring. It just really allows us to do evaluations very quickly. It also helps when we want to determine the domain of a function or the x-intercepts of a function. There's a lot of uses for factoring techniques. Although you're never told that, honestly, when you begin in algebra, the reality is that the power of factoring becomes more and more important as you move through mathematics, not less. It seems so weird that you spend all this time dealing with polynomials, like these guys right here. You spend all this time in algebra dealing with polynomials, and nobody ever tells you why. Here is the secret. Get ready for it. Every single function, well, I shouldn't say every single, I'll say every analytic function, or every function that you normally deal with, can be written as an infinitely long polynomial. If nobody's ever told you that, it's pretty fair that they didn't. Usually people don't know that if they're teaching K-12, but it is actually true. Every single function that you normally deal with, like e to the x, that exponential function is actually an infinitely long polynomial. Just like, even if you haven't taken trig, let's just pretend that you have for a second, just like the sine of x can be written as an infinitely long polynomial. Just like the square root of, let's say, actually maybe I won't do the square root because there's something a little bit wonky about that, but let's say something like that. That rational function can be written as an infinitely long polynomial. So each of these cases, we have polynomial representations, which means that we might be able to factor them. And so therefore, factoring ends up being supremely important as we move forward. You spend all this time working on it without knowing why. That's why. Now, I did tell you that we were going to go ahead and review some factoring techniques. The factoring review that I'm going to do is going to be built inside very high-level problems because you've already seen all of algebra up to this point. You know how to factor polynomials or trinomials or factor by grouping or factor difference of squares. So you know those techniques, but you may not have seen them in very advanced examples. So I'm going to combine a review with advanced examples. So let's take a look at this statement right here. We're asked to simplify that expression. The very first thing you're going to do is follow the order of operations. And the order of operations just says, look at the innermost group, and the innermost group here is this guy right here, and see if that can be simplified. And that can be simplified. So right from the get-go, I am not using factoring techniques, I'm using simplification techniques. What I'm going to use here is this nice property or law of exponents. If you have the product of two exponential expressions that have the same base, so b to the m times b to the n, then the result will be that same base raised to a power which is the sum of those exponents. So it is raised to the m plus n power, where this is the m is the exponent of the first, n is the exponent of the second expression. So here we have two exponential expressions multiplying. They both have the same base. You can see it right here. This has a base of 2. That has a base of 2. So we could use that law of exponents off to the right to say that this expression is equal to 2 raised to, and we're going to add their exponents together. 2 raised to the x squared plus 5x plus 6. Very nice use of a law of exponents. Now, I still focus in using the order of operations from good old arithmetic. I focus in on this and I say, is there anything else I could do to make this a nicer expression? The reality is factoring often makes things nicer expressions. Again, we use factoring in language all the time. You don't say, hey, I've got this, I've got this bubble gum, and my friend has bubble gum, and his friend has bubble gum, right? You would just say, the three of us have bubble gum, right? So in reality, that's part of simplification. You're simplifying your language. So let's simplify by factoring that trinomial. And you should recall, but if you don't, I'll remind you here, that when you're factoring a trinomial, like, let me highlight it, like this guy right here, if it has a unit coefficient, in other words, the lead coefficient of x squared is just a simple little 1, then you want to factor this into the product of two binomials such that it looks like this, x and an x, and you want the numbers that are inserted right here to be factors of 6. So you want them to multiply up to that 6 right there. So I'm just going to put a little dot there, meaning we're multiplying them. So I need two numbers that multiply to 6, and simultaneously, we want them to add to 5. Now, if you don't know why, then honestly, this might not be, a college algebra course might not be the right course for you. You should know why. So two numbers that multiply to 6 and add to 5 are 2 and 3. So let's go ahead and in those positions, put a positive 2 and a positive 3. If you were to multiply that binomial back out, you would see, or those binomials, sorry. If you multiply that product of binomials out, you could see you get an x squared plus 2x plus 3x plus 6, which is x squared plus 5x plus 6, which is exactly what we have up here. All right, so following the order of operations, I've talked about, I don't really dive into a deep dive on a review for unit coefficient trinomials like that. I just kind of remind you, hey, you want to find two numbers that multiply to the constant and add to the coefficient of x. That's if it's a unit coefficient. That's a different technique otherwise. Now, we are done inside this parenthesis because honestly, there's nothing else you can do in here. So then I ask, well, if I'm done there, using the order of operations, which tells us to work on the innermost grouping symbols, and then once you're done there, you can work on exponents. Well, these exponents, there's not much I can do with them. So I'll hop outside of this and I'll look at this exponent. And we have a law of exponents that tells us that if you have b raised to the negative n power, that is the same thing as 1 over b to the nth power. So I'll go ahead and rewrite that x plus 2 to the negative first as 1 over x plus 2 to the first. Let me just write this in here. I'll rewrite my grouping symbols as brackets just because when I have groups within groups, I think logically it makes more sense to have different grouping symbols. So the exponent I'm going to write as 1 over x plus 2 rather than x plus 2 to the negative first. And I'll also use yet another law of exponents here. The law of exponents I'm going to use next is that b raised to a power is going to be that base raised to the product of those two powers. Again, I'm not going to prove that because that should have been proven 2 courses ago at the very minimal, or at the very least for you. So, but the reality is powers to powers multiply. So this means that this expression we're looking at becomes 2 raised to the power of x plus 2 times x plus 3 times 1 over x plus 2. Again, I'm raising everything powers to powers, and so those powers will multiply according to this law of exponents to the right there. Well, now, if you're multiplying these together, honestly, I could have written this much more cleanly. I could have said this is the same thing as x plus 2 times x plus 3 over x plus 2. And now you can see the x plus 2's cancel beautifully. And this is now just a simple 2 raised to the x plus 3rd power. This is acceptable as a simplified form of that original statement. And we reviewed a little bit of factoring in the process. Is this the only way you could write this? No, not at all. There's actually one other way you could have written this by using a law of exponents. The law of exponents you could use here is b to the m plus n is the same thing as b to the m times b to the n. We've actually seen this law right up above. We just wrote it backwards this time. But we can apply that law and say, oh, this is the same thing as 2 raised to the x times 2 raised to the 3rd, or in other words, 8 times 2 to the x. But to be honest with you, most instructors, myself included, would be super happy if you got down to this and left it like that. I think that's a perfectly fine form, although this form right here is definitely equivalent. You're more than welcome to make that move. I just think it looks uglier. I think it's much easier to write it as just 2 raised to the x plus 3rd power. All right, so that is a very very low-level quick review of factoring trinomials with unit lead coefficients. But what if we're asked to factor a trinomial, which is what this is? It has 3 terms, and it's a polynomial, so we call it a trinomial. What if we're asked to factor a trinomial that does not have a lead coefficient of 1? Well, there are a couple things going on in this problem. Whenever you go to factor something in mathematics, you start by the simplest way to factor something. Again, think about the language example we had earlier. Student A is wearing pants, student B is wearing pants, and so on and so forth, all the way down to student Z is wearing pants. The easiest thing we could do is just say, hey, everybody here is wearing pants. All these people, A, B, C, all the way to Z. That's called factoring out the greatest common factor. We're just taking the thing they have in common and ripping that out and saying they all have this quality. So using that same mindset or that same idea, in this case, you could look through each of these terms and notice each of these terms here actually does have something in common, or they all have something in common with each other. They all have an X in common. X here, an X here, and an X there. The trick to factoring out a greatest common factor when it comes to variables is to factor out the greatest common factor, or I should say the lowest powered occurrence of their common variable expression. Let me write that down. So there you have it as a best practice. Factor out the lowest powered version of all common factors. Now, as far as constants, like coefficients here, 12 and 19 and 18 do not share anything other than 1 in common as far as factors go. So constants, they don't have anything in common. But x's, they do have something in common. So I'm going to say this is equal to, and then I will discuss how to figure out what power of x to factor out. I'm going to factor out some power of x. Let's look through each of these to see what's the lowest powered version of x. Well, if you look at the first term here, I'll write it in blue up above, this by the law of exponents is actually x raised to the 2n power. Let me zoom out a little bit just so that my handwriting isn't too terrible. Times x to the second power. Again, the next term in line is actually x to the n times x to the second power. Again, just because of the law of exponents, where you say x to the m plus n is equivalent to x to the m times x to the n. Finally, that last guy right there is just an x squared. But if you notice, each of these has an x squared in common. That's the lowest powered version of x they have in common with each other. So let's go ahead and factor out an x squared. Remember, if you don't remember this, is good advice. Factoring is division. That's what factoring is. I'm going to write that down. Factoring is division. That's super important because when you get to very complex expressions, you want to remember that you're actually dividing off an x squared when you're factoring x squared off of something. So if you imagine this here, just take a look at each of these terms. We have a 12x to the 2n times x squared. We have a 19x to the n times x squared, and we have a negative 18x squared. If I were to take this first term and divide off an x squared, I'd be left with a 12x to the 2n. Likewise, if I go to the second term and I divide off, because I'm factoring, if I divide off that x squared, I'm actually factoring or dividing that term by x squared, and you'll be left with a positive 19x to the n. And finally, on the last term there, if you factor off an x squared, you're again just dividing off x squared, and that would be a negative 18, which is left over after the division. Now this is a very nice trinomial in the end. We might be able to factor that trinomial. And I just dislike that parenthesis was all the way over there, so I'm moving it. Now to factor this, I need you to understand that there's a method that will pay you dividends by knowing it as you move forward in mathematics. The method is called a U substitution method. This is a method to really kind of pull together commonalities or common factors that occur within mathematical statements. You can, if you don't like these letters, you could say, well, you know what? I would rather this be like something like an x squared there and something like an x there. Well, you can almost force it. You could say, I'm going to let, I'll do this off to the right-hand side, let u equal x to the n. Now, you may not understand why I'm doing that yet, but you're about to see why. Because if u is equal to x to the n, and you want to get x to the 2n, you want to find out what that is? Well, x to the 2n is the same thing as x to the n squared. That's what x to the 2n is. I'll write it over here. Oops. Except for I have to actually write it properly. But that's just taking x to the n and squaring it. And remember, x to the n is u. So u squared is the same thing as x to the 2n. This is called a u substitution. A very, very powerful technique that ends up helping you throughout all of calculus. So let's see here. If we do that, I have an x squared that's just hanging out front. I'll leave that alone. And then I have a 12. Instead of x to the 2n, I'll call this u squared, because that's what x to the 2n is. It's a u squared. Plus 19u, again, because x to the n, well, that's equal to u. And then minus 18. Writing it like that really allows you to see that this might just factor. This might be a factorable trinomial. And it kind of declutters the problem in a way. Now, the method I'm going to use to factor this trinomial is called the guess and check method. Some people call it the trial and error method. There are a lot of methods to factor trinomials like this, where the lead coefficient, this guy right here, is not 1. There's the AC method, the box method, the diamond method. There's a whole bunch of them. However, I do something called the guess and check or the trial and error method because it gives you a more natural understanding of how factoring occurs. The one thing you do not want to do as you move forward in mathematics is to factor this by grouping. That's the basis for a lot of factoring techniques, but you don't want to constantly factor by grouping. That's just slow and it doesn't help you out in the long run. So let's go ahead and shed that skill, at least for trinomials, and let's do something called guess and check. So how does the guess and check method work? Well, if this trinomial, 12u squared plus 19u minus 18, if that factors, then if I plug a u right here and a u right here, there are some missing coefficients. Remember, when you do the binomial distribution, you'll get whatever this coefficient is times u times whatever coefficient this is times u. So you'll have a u squared times the product of those coefficients. All right. So I need those two coefficients to multiply to become 12. So start listing out what are the possible factors of 12. For example, what are two numbers that multiply to 12? 1 and 12, obviously. 2 and 6, obviously. And 3 and 4, again, obviously. Those are the only combinations that I can work with. Now on the back end, let me use a different color for that. In those spots right there, I need two numbers that will multiply to a negative 18. But the deal here is I don't really care about the negative part yet. I just care about the fact that I need two numbers that multiply to an 18. I'll deal with the negativity of it a little bit later. So let's list out some products or some factors, of 18. Well, 1 and 18. But in this case, by the way, you want to keep track of order. So either 1 and 18 or 18 and 1. I didn't worry about that with my blue ink because I'm really just saying those are concrete positions. This will, if it's going to be 1 and 12 on the U, the 1 will be on this guy and the 12 will be on that guy. But once I anchor those in place, my green ink is the one that I'll swap order on. You'll see what I mean as we move forward. What are what's another factor of 18? Well, 2. 2 and 9, or again, 9 and 2. How about another factor? 3. 3 and 6, or 6 and 3. Are there any other factors? Well, 4 doesn't go into 18, 5 doesn't go into 18, 6 does, but we already have it. And once you say that, then you're pretty much done. There's nothing else you need to do. Once you get to a repeat of something that you've already listed, there's no other work you have to do. So those are my candidates of how this is going to possibly factor. The guess and check method may seem very long-winded to begin, but it's not at all. It's very fast. It's very fluid. It's very heuristic, which means it requires you to practice it to get really good with it and to really kind of get a technique going that works for you. But it is actually a very simplistic method and works wonderfully. To showcase what I'm going to do here, I'm going to write down one candidate combination. So one candidate combination is the following. We could have had one U and a 1 and a 12U and the 18. All I did was take this first row here, basically. Okay. And if this works, well then notice the product of 1U and 12U is 12U squared, which is exactly what we wanted. And notice the product of 1 and 18, well, that's 18. We need it to be negative, but we'll worry about that later. So the first and last numbers basically work. Maybe I should point at that one. But now we need to look at the inners and outers. That's what I call it, the inners and outers. So just to let you know, by design, the first and lasts will always be the 12 and the 18. 1 times 12, well, that's always 12. 2 times 6, that's always 12. 3 times 4, that's always 12. And likewise, 9 times 2, always 18. 3 times 6, always 18. So we've already set this up to where the product of the first two terms in each of those binomials is going to be 12u squared. And we've set this up to where the product of the constants will always be an 18. So that is no longer a concern. What we do need to worry about, so I'm going to erase these now. What we do need to worry about is what are the products of the inner and outer numbers. So for example, in this case, we have an 18u and a 12u. I'm not going to say plus, I'm just going to say 18 and 12. 18 and 12u. And the question is there any way to combine 18u and a 12u to become a 19? No. Adding, subtracting, no matter what you do, that will never become a 19. So I know immediately that this row containing the 18 and the 1 is not a candidate. Again, this is incredibly long-winded if you go through slowly like this, but it's actually really fast once you get used to it. For example, out of experience, I would look at this polynomial, this trinomial here, 12u squared plus 19u minus 18, and I'd say, okay, great. What are the factors of 12? Well, I know 1 and 12 multiply to 12, but I'm not going to worry about that. I'm going to start either with a 2 and a 6, or better yet, with the 3 and the 4. To me, a 3 and a 4 is a really nice, they're kind of close to each other. I don't know why. They're smaller numbers. I kind of like that. And same thing with the 18. The 18, two numbers that multiply to 18, well, of course, it's 1 and 18. But again, those are so large, I don't like those. So I'm probably going to deal with either the 2 and the 9 or the 3 and the 6. So these groups right here. So this is how I start. I just say, okay, well, let's pretend that we're going to look at the 3 and the 4 situation. I'm going to erase my work over here. And now I'm just going to try the start here, 2 and 9. So I'll throw a 2 right here and a 9 right here. Now, by design, it should be the other way around. 3u times 4u is always going to be 12u squared. And 2 times 9 will always give me the 18. So I'm not concerned about those. I'm concerned about the outers and inners. The outer is 27u. The inner is 8u. Is there any way to combine 27 and 8 to become a 19? And the answer is yes. That, by the way, I did not know that this was the way it was going to factor. I just immediately kind of went for a different combination other than 1s and 12s and 1s and 18s. I kind of wanted to do stuff or work with numbers that were a little more closely aligned. So the trick here is that I want it to be 27u minus 8u, because that would give me a positive 19u. Okay, well, to get a minus 8u, that has to be a negative right there. And to get a positive 27, that has to be positive right there. Notice negative 2 times 9 is negative 18. That is how this factors. So again, when I do the guess and check, it's actually pretty darn quick. In fact, I generally do it like this. I know 12 is going to split into either 3 and 4 or possibly 2 and 6, but I'm just going to write the 3 and 4. And I know 18 breaks into 1 and 18, 2 and 9, and 3 and 6. But again, I'll likely try 2 and 9. And then I just do this, 3 and 4. I look at, this is either a 2 and a 9 or a 9 and a 2. And we deal with outers and inners. So outers, 3 and 9 versus inners, do a different highlighter color, 2 and 4. 3 and 9, that's 27. 2 and 4 is 8. 27 and 8 can be combined to become 19. It's very, very fast. And then I just go ahead and move those. Let me erase this. I move those numbers to be in a position where they fit inside my trinomial factorization. So this will be a 3u minus 2 and a, let's see, 4u plus 9. Double check over here. Yep. All right. Now, here's the deal. You can't stop here. I know we were asked to factor, and this looks like it's completely factored, but you should note there's something wrong. Specifically, these two variables were not in our original expression. We started in the world of x's, not u's. So let's figure out what u is. Oh yeah, u is equal to x to the n. So we're going to resubstitute in the end and let u equal x to the n. So this is 3x to the n minus 2. And again, 4x to the n plus 9. You could do this guess and check method all day long. It's a really nice method to work with. Now, again, if this were an intermediate algebra or an elementary algebra class, I would spend a week covering how to factor using the guess and check method. I'm assuming that you're advanced enough at this point to be able to catch on. Practice on your own. That's a good way to do it. Build whatever trinomials you need and just practice on factoring using the guess and check method. Now, as a reminder, you should know the difference of squares, the sum and difference of cubes formulas. Those should be just in your brain, embedded in your brain. Difference of squares is such a powerful formula, and it's so underrated. I write it slightly differently than most people. I write it with, instead of a squared minus b squared or x squared minus y squared, I use capital F and capital L. The reason why is because I found that through years of teaching that if you teach it with x squared minus y squared is equal to x minus y times x plus y, while that is true, it totally is true. It does factor like that. People get a little confused when they're given an expression like this, 4x squared minus, I don't care, 16y squared or something like that. Because the theorem they've been taught has x's and y's as well, it kind of confuses them. So instead, I like to teach it with two letters that never get used, capital F and capital L. Capital F stands for the first object, capital L stands for the last object. So you have a first object squared minus a last object squared. I'll even highlight those. First object squared minus last object squared will always factor to be the first object minus the last object times the first object plus the last object. Again, a very, very important formula. I'm not going to prove it here. I have that in my elementary algebra videos, the proof of that. So you're more than welcome to find those and review the proof if you want. But the proof is pretty much just multiplying out the right-hand side. Again, I'm approaching this video and these lectures at a higher level than what you would get if you were just learning this topic. So it is assumed you know all these factorization techniques. To factor something like this, which is very common to get expressions like this in a calculus course, you want to notice patterns. The pattern here is you have some object being squared minus another object being squared. That is a difference of squares. A lot of people will actually multiply this stuff out, combine like terms, and then refactor in the end. I'm telling you, that's a supreme waste of time. If this is, let me use a different ink here, some first object being squared minus some last object being squared, I know that that factors into the first object minus the last object times the first object plus the last object. Well, what is the first object? The first object, I'll write it in green, is 8x squared plus 7x plus 1. And we're losing from that the last object, which I'll write in blue. The last object is 8x squared minus 7x minus 26. That's first minus last. First minus last. And we need to multiply that by first plus last, because that's how this is factoring. So first, again, is just that green ink, and the last is the blue ink. Now you may look at that and say, man, that's a whole lot of handwriting. It is, but actually it cleans up very nicely. Remember, this negative right here, it's critical when you have subtractions in mathematics that whatever you're subtracting off, you have in a parenthesis sign, because, or in a group, I should say, because you're subtracting that entire group. Everything in there you're subtracting. You're subtracting each of these. In other words, that negative will distribute. It's very, very important that you remember that. So if we remember that, that first group there, that first factor that you see in green and black, we have 8x squared, but we're going to lose an 8x squared, so there's no more x squareds. We have a 7x, and we're going to lose a negative 7x, or in other words, 7x plus 7x is 14x. We have a 1, and we're going to lose a negative 26. That'll be 1 plus 26, or in other words, 27. Now we go to the other group. And in the other group, I have an 8x squared plus 8x squared, so that'll be a 16x squared. And then we have a 7x plus a negative 7x. Well, those will cancel beautifully. And then we have a 1 plus a negative 26, which is a minus 26. So 1 minus 26 is a minus 25. And people say, wow, I can't believe it. That's completely factored. That's not completely factored. It's not completely factored because you need to figure out, do each of these factors have something like this first factor? Do the two terms in that first factor have anything in common? The answer is no, they don't. Can you factor that? No, you can't. The next factor, do those two terms have anything in common? The answer is no, but that is a difference of squares. That is a 4x being squared, let me write that down, minus a 5 being squared. So that will factor even further. So you get this 14x plus 27, and then the difference of squares, 4x minus 5 and a 4x plus 5. And there you go. That is the full factorization of that difference of trinomials that we started with. You are more than welcome to have multiplied all that stuff out, like squared both those trinomials and then subtracted one from the other, combined like terms and all that fun stuff. But I'm telling you, if you did that, you would have a really hard factoring problem in the end. Actually, something that you probably wouldn't be able to factor because you wouldn't be able to see how it factors. So noticing that you're starting with a difference of squares is incredibly powerful. When you start problems, always take a moment to look for a pattern. Take a moment to look to see, is this like a pattern I've seen before, a difference of squares, a sum of cubes, whatever it may be. Since you've already gone through all of algebra, except for college algebra here. I'd like to now start talking about how those mental math tricks are done and how you can start using them to your advantage. You've probably seen them on YouTube or something like that where somebody can do some massive computations very quickly. And I'm not going to teach you how to do all of them or even half of them, to be honest with you, but there's one very special trick that you can actually do fairly quickly. Let's go ahead and talk about this, and you can read my sentences up above. The last one says, one such trick is no trick at all, but instead a beautiful use of factoring. So let's evaluate this without the use of a calculator. Obviously, you should not need a calculator to multiply 6 against 14. That would be 60 plus an extra 6 times 4 or 24, so that'd be 84. That is not mental gymnastics. You should be able to do that. By the way, if you're wondering how I did that, I think most people don't wonder. I think most people understand. But if you're wondering, if you're like, wait, what did he just say? I do my math this way. That's 6 times 10 plus 4. And the reason why I do it that way is because 6 times 10 is very easy. That's just 60. And then 6 times 4, well, that's not too bad. That's just 24. And then you add those results up. But another way we could have done this is we could have found the center of these numbers. So if you think about 6 and 14 on a number line, I'll actually draw a number line here. The number that's halfway between those two, or in other words, the average between those two, is 10. The way you would find the average, by the way, is you would just add 6 and 14 and divide by 2. 6 plus 14 is 20, divide by 2, and you would get the average, which is 10. So you could say that instead of 6 times 14, you're actually looking at 10 minus 4 times 10 plus 4. In other words, you stood at the center, that's what 10 is, and you're wiggling from that center by a distance of 4 in both directions. So 10 minus 4, 10 plus 4. But if you notice, that's actually going to be a difference of squares. That's a factorization of a difference of squares. So this is going to be 10 squared, the first item squared, minus 4 squared, the second item being squared, which is 100 minus 16, which is 84. Now you might say, well, that's way too much work. I don't want to think about how you did that. You should actually think, because you're in college algebra, which means that you're going to be expected to do things outside of the box. You have to think outside of the box in a college algebra course, and especially in calculus. You really have to be on your toes in calculus. So get used to these weirdnesses. Let's take this up a little bit. What if, without a calculator, we're asked to compute 96 times 104? Yeah, you could totally do the stacking method, right? Oh, you can look like an arithmetic student. Oh, okay, 6 times 4 is 4, right? You can go through and do all that stuff. But you don't have to. What's smack dab in the center between 96 and 104? If you said 100, you're absolutely correct. This number, this product, is the same thing as 100 wiggled by 4 down and 100 wiggled by 4 up. But again, that's like x or f minus l times f plus l. It's a difference of squares. It is 100 squared minus 4 squared. 100 squared is just 10,000 because it's 4 sets of zeros, right? You have 2 sets of zeros right here, and you're squaring it so you get another couple zeros on there. So that's 10,000 minus, whoops, you're probably yelling at me, minus 16. That's 9,984. Now, to be honest with you, you don't have to write all this stuff out to do that. If somebody came in the room and just said, man, I'm working with this crazy computation and it is, I'm just going to change it up slightly. It's 997 times 1003. And they told me to do that. You would say, well, that's like 1,000 wiggled by 3. So this would be 1,000 squared minus 3 squared. Again, because it factors, this was 1,000 minus 3, and this is 1,000 plus 3. So you could say, well, that's 1,000. Just in your head, that's 1,000 squared. 1,000 squared is, you have 3 zeros on 1,000. You're going to put another 3, so that's 1,000,000, and then minus 9. And so you could tell that person, oh, you're looking at 997 times 1,003. Oh, yeah. So let's see, that's 999,991. And your friend looks at you and they say, how the heck did you do that so quickly? And you just say, I memorized you didn't go that far in your multiplication tables? But in reality, what you're really doing is you're just quickly throwing some zeros together and subtracting 9. Very, very nice trick. But what if you don't deal with 100s? What if you're centered at something that's not so nice, right? Well, if you're centering at, let's say, a 37 or a 73 or something like that, then you might as well just grab a calculator, because unless you know what 73 is squared, then I wouldn't bother. But in this case right here, 48 times 52 is still doable. That's like 50 wiggled by 2, right? 52 down and 52 up, which is 2,500, because that's 50 squared, minus 4, or in other words, 2,496. A great use of a difference of squares formula. So I like to do these because I think it's so important that you know how to use these types of computations outside of just variable manipulation. All right, enough of that fun. Let's go back into formulas. Just as a reminder, you have sum and difference of cubes formulas, and these are supposed to be in your brain pan, so make sure that you do remember them. I don't prove them here because, again, they should be proven to you either in your elementary algebra course or your intermediate algebra course, but they're really assumed content in your college algebra course. The formula that likely you're going to commit to memory is first cubed plus or minus last cubed is the same thing as first plus or minus last times the quantity first squared, and this is, I kind of look at it here, I say, oh, times, and then it's going to be this thing squared, and then it's going to be opposite of what you add here. So if it's a plus minus, it's a minus plus, and then the product of first and last here, and it always ends with a plus the last item squared, and you can see that right there. So this is the sum and difference of cubes formula, and it matches very nicely with my difference of squares formula, the way that I write it. And the reason why I say that is, if you look at my difference of squares formula, I write it always like the following. F squared minus L squared is, I'll take this first item, I'll take this sign, and I'll take this last item. And then I'll take, again, that first item, the opposite of that sign, and maybe I should do that in red. And then the last item. Again, that's the difference of squares. But the difference of cubes is very similar, actually. Difference of cubes, I'm going to take that first item. I'll take the sign. I'll take the last item. Now, because of the difference of cubes in this case, I need to multiply that linear term right there, or that linear factor, by a quadratic. In other words, I have to have something with an f squared in it. So I then take this guy and I'll square it. I'll take the opposite of that sign, and then I'll take the product of the f and the L here, and then I'll finally add that last term squared. And then finally, first cubed plus last cubed is the same setup. I'll take this first object, I'll take this sign, I'll take this last object. I know because it's a sum of cubes that I'll need a square on this f, so I'll square this f. I'll take the opposite of this sign, and then I'll take the product of f and L, and then I always, at the very end, add the last item squared. The structure of it's very, very similar to the structure of the difference of squares. You can see that in all three cases, they do match up very nicely. If there's a minus, it's a minus. If there's a minus, it's a minus. If there's a plus, it's a plus. Okay. All right. So those are the sum and difference formulas for the cubes. let's go ahead and use them. We have x to the 6n minus y to the 9n power. That is actually a difference of cubes. If you can't see it, you should always try to rewrite it as a difference of cubes. You should say, well, could that be written as something cubed minus something else cubed? And the answer is yes. That's an x to the 2n being cubed, and this is a y to the 3n being cubed. Again, because of that law of exponents, which will haunt you for all of mathematics, b raised to the m raised to the n is the same thing as b to the m times n. So x raised to the 2n raised to the third is x to the 2n times 3, or x to the 6n, and so on and so forth. This is definitely a difference of cubes, so let's go ahead and factor. It'll be the first object minus the last object, and now we'll go ahead and I just kind of, from this point forward, just focus on this, and I say, okay, well, let's see, I need to take that first object there, let me point an arrow at it, and I'm going to square it. That's going to be x to the 4n. And then I'll take the opposite of the sign. So I'll write that as a plus. I'll use red just to showcase that. And then I'll take the product of this first object and the last object. So I have x to the 2n and y to the 3n. And then finally, always add the last term squared. So y to the 6n. And there you go. That is the fully factored form of this. Now you might ask, wait, how do I know that that doesn't factor further? You don't, actually. You have to kind of look at this and see, is this factor here, x to the 2n minus y to the 3n, is that a sum or, well, it's definitely not a sum. So is it a difference of squares? No, it's not. There's a 2 there, but that's not an even number, so it cannot be a difference of squares. Well, is it a difference of cubes? Well, I don't have something cubed there. I can't say that's a cube. So this is totally a cube, but the x is not. So it's not a difference of cubes. So this is what we would call prime. It cannot factor any further. It is stuck. And then you ask, well, what about that trinomial? Can that factor? And here is the sticky wicket in this problem. Normally, when you use the sum or difference of cubes formula, if you start the problem by factoring out the greatest common factor if they have one in common, which these two do not. But if you start the problem by factoring out the GCF, then the trinomial you get right here will be prime. It will not be factorable. So always be aware of that. You will be in pre-calculus able to factor that over the imaginary numbers in the complex number system, but for now, if you're just entering into college algebra, we're just talking prereqs, and so right now, you will not have to factor that trinomial off the back end. The final example I have in this video is just to showcase that you don't need to even have a function you know how to work with to do a sum or difference of cubes, or even a difference of squares. So let's suppose, which is probably the case, that you have not had trigonometry, and you do not know what this wicked-looking sine function is. I'll give you one piece of information that helps out here. This notation is the same thing as saying I have a function called sine of x and we're cubing it. That's what that notation means. And then we have a 3 cubed off the back end there. So just letting you know that that's a special notation usually reserved for the trigonometric functions. You don't need to know what the sine function is to take advantage of that. So here we have a sum of cubes. It's a sine being cubed plus a 3 being cubed. Using my sum of cubes formula, I will take the first item, which is a sine of x, plus the second item, which is a 3, and I'll multiply that by the first item squared. Now I'm just letting you know, the shorthand for squaring a sine function is to put the square after the n in a superscript. And then I'll take the opposite of this, which is a minus, and I will multiply 3 against sine, so 3 sine of x. And then finally, plus that last item squared. That is the complete factorization of this expression. And you didn't need to know trigonometry to do it. This is actually pretty nice. In fact, I could have just given you a silly function you don't even know what it is. I could have said we have this happy face cubed plus 27. All the mathematics is exactly the same. It's Oops, except you have to be able to draw a happy face. That would be happy face plus 3 times happy face squared minus 3 happy face plus 9. So you don't really need to even know the function to be able to use the sum or difference of cubes formula or the difference of squares formula. The only other thing I want to remind you of is there's no such thing as a sum of squares formula. There's no way to really factor a sum of squares over the real number system. You can factor a sum of squares over the complex number system, which you will do in a pre-calculus course, but generally not a college algebra course. All right, that does it for this video. I will see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Names for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.